Spring 1927, Highland Park, Michigan, Chrysler Engineering Department. Carl Breer, Chrysler's chief engineer, stared at another failed clutch assembly from the new Chrysler 70 sedan. The problem was maddeningly simple. Oil leaking from the engine was seeping into the clutch mechanism, causing it to slip. Drivers complained their cars lurched and hesitated. The clutch pilot bearing, a bronze sleeve bushing pressed into the flywheel, was supposed to align the transmission shaft, but its location, buried deep between engine and transmission, made it practically inaccessible. You couldn't grease it from outside. You couldn't service it without disassembling half the drivetrain. Breer had tried everything. Tighter seals, they leaked anyway, grease-packed bearings attracted more oil, graphite bronze bearings wore out quickly. Nothing worked. The problem haunted him through 1927 and into 1928. Then one day, Breer had an idea that seemed absurd. What if you could make a bearing that held its own oil supply internally? A bearing that was essentially a metal sponge soaked with lubricant. Everyone knew this was impossible. General Motors had tried making bearings from compressed copper and graphite powder in the early 1920s. They'd failed. The bearings crumbled or the oil wouldn't stay in the metal. The concept was dismissed as impractical. But Carl Breer was stubborn. He hired two specialists, William Sherwood, a mechanical engineer, and Bill Calkins, a metallurgist. Their task, make the impossible bearing work. By 1930, they had succeeded. The resulting invention, called oilite, would revolutionize bearings worldwide. More importantly for history, when World War II began and American tanks began overheating and seizing from inadequate lubrication in North African deserts, oilite bearings would prove to be the solution that kept armor moving when conventional bearings failed. This is the documented story of how Chrysler engineers turned copper powder and vacuum chambers into self-lubricating metal, creating a technology so effective it's still manufactured today, nearly a century later. The Chrysler 70, also called the B70, launched in 1924, was Walter Chrysler's first car under his own name. A six-cylinder automobile priced to compete with Ford and GM, it sold well enough to establish Chrysler Corporation as a viable automaker. But by 1927, warranty claims were mounting. The clutch problems weren't catastrophic, cars didn't break down, but they were embarrassing. Drivers reported unpredictable engagement, slipping under load, and premature wear. Carl Breer traced the problem to the pilot bearing, a small cylindrical bronze bushing that supported the tip of the transmission input shaft where it entered the engine's flywheel. This bearing had to operate in a hostile environment. No external lubrication access, buried between engine and transmission, oil contamination, engine oil constantly leaked past seals, high loads, supporting transmission shaft weight plus clutch engagement forces, inaccessible location, required transmission removal for service. Traditional solutions didn't work. Grease-packed bearings attracted oil, making clutches slip. Dry graphite bearings wore rapidly. Oil bath bearings were impossible. There was no sealed chamber. What Breer needed was a bearing that carried its own permanent oil supply, protected from external contamination, releasing lubricant only when friction heated during operation. Such a bearing didn't exist, so Breer decided to invent it. Carl Breer hired William Bill Sherwood and Bill Calkins specifically for this project. Sherwood understood mechanical engineering and manufacturing processes. Calkins brought metallurgical expertise, knowledge of how metals behave at different temperatures and how alloys form. They started with what was known: powder metallurgy, the process of forming parts from metal powders. This wasn't new. Industries had used sintered metal powders for years to make parts that were difficult to machine or cast. The process basics: 1. Mix metal powders, usually copper, tin, graphite. 2. Press in molds under high pressure to form shapes. 3. Sinter in furnaces at high temperature below melting point to fuse particles together. Result: solid metal part without casting or machining. General Motors had attempted adding graphite to copper tin powder to create self-lubricating bearings in the early 1920s. The graphite, naturally slippery like pencil lead, was supposed to provide lubrication, but the bearings failed. They were too porous, too weak, or the graphite didn't provide adequate lubrication under high loads. Sherwood and Calkins took a different approach. Instead of relying on solid graphite for lubrication, they would create porous metal that could hold liquid oil internally. The key innovations: controlled porosity. By carefully selecting particle size and sintering temperature, they created metal with interconnected pores throughout the structure, like a hard metal sponge. Oil impregnation. They placed the sintered bearings in a vacuum chamber, evacuated all air, then flooded the chamber with oil and restored atmospheric pressure. The pressure difference forced oil deep into every pore. Capillary action. The microscopic pores acted like capillaries. When the bearing heated from friction, thermal expansion pushed oil to the surface. When it cooled, capillary action pulled oil back into the pores. By 1929, Sherwood and Calkins had working prototypes. The bearings held 25 to 30% oil by volume. Roughly one-third of the bearing's total volume was oil stored in pores. Wiped clean, they appeared completely dry, but under friction and heat, oil appeared at the bearing's surface, providing lubrication exactly when and where needed. Sherwood filed patent applications in 1929 and 1930 through his own patent-holding company. The patents described the vacuum impregnation process, evacuating air, submerging in oil, pressurizing to force oil into pores. The first oilite bearings appeared in 1932 Chrysler automobiles, specifically in the floating power system, Chrysler's innovative engine mounting that reduced vibration. The bearings solved Breer's original clutch problem perfectly. Installed in the pilot bearing location, they provided continuous lubrication without external service. The oil trapped in the porous bronze couldn't escape to contaminate the clutch, but friction heat brought it to the bearing surface during operation. But oilite's applications quickly expanded beyond clutches. Water pump bearings, operating in hot, wet environments, leaf spring shackles, previously squeaked constantly. Oilite eliminated noise. Starter motor bushings, high-load intermittent operation, generator bearings, continuous rotation with limited maintenance access, distributor shafts, precision applications requiring consistent lubrication. Sales exploded. Chrysler reported selling 7 million oilite bearings in 1932, the depths of the Great Depression. By 1933, sales reached 18 million. Oilite became a profit center for Chrysler during years when automobile sales were collapsing. Walter Chrysler approved establishing the Amplex Corporation and its oilite division to manufacture and sell these bearings. The division quickly expanded beyond automotive applications into industrial equipment, marine engines, and aerospace. By 1935, Amplex operated a 5-acre, 9-story plant at 6501 Harper Avenue in Detroit, with nearly 200,000 square feet of floor space. The facility produced not just oilite bearings, but an expanding range of sintered metal products: gears, structural parts, filters. One of Amplex's unexpected innovations came from another Carl Breer problem-solving session. Gasoline in the 1930s contained sediment and impurities. Gas tanks used glass sediment bowls with wire mesh filters to prevent debris from reaching carburetors. But the wire mesh was expensive and didn't filter finer particles. Breer suggested making filters from sintered metal, same porous structure as oilite bearings, but without oil impregnation. The pores would trap sediment while letting gasoline flow through. Initial attempts failed. The engineers tried making sheet steel strips with pores, but couldn't achieve uniform pore size. Then they cracked it. Use powder of uniform particle size, sinter it flat, and the resulting filter had consistent pore structure. The sintered metal gasoline filter was so effective that it could even separate water from gasoline. Breer recounted a legendary demonstration. One of our executives ran out of gasoline in the country one day. He stopped at a nearby farmhouse and asked for a small pail of water. The farmer graciously complied and saw the executive pour water into the gasoline tank. To the farmer's astonishment, our executive stepped on the starter and away he went. What really happened was that our new strainer was so effective that it had let gasoline through, but not the water. When the water was added to the gasoline tank, it raised a little gasoline left in the tank to where the strainer would let it through, enough to let him make it to the nearest gas station. The Army tested numerous fuel filters for military vehicles in the late 1930s. Amplex's sintered metal filter was the only one that met their requirements. It became standard on military vehicles through the 1950s, eliminating the need for glass sediment bowls that could shatter in combat conditions. When Germany invaded Poland in September 1939, European nations urgently turned to the United States for military production. Britain and France placed large orders for trucks, aircraft, and armored vehicles, seeking to supplement their strained industrial capacity. At the same time, the U.S. Army was rapidly expanding and modernizing, anticipating possible involvement in the conflict. New armored designs were under evaluation, including the M2 medium tank and early development models that would later evolve into the M3 Lee Grant and ultimately the M4 Sherman. Field trials, particularly those conducted in hot, dusty environments, highlighted a broad range of maintenance and reliability challenges. Tanks proved mechanically demanding machines, operating under conditions that pushed every moving component to its limits. Armored vehicles faced an especially hostile operating environment. Extreme heat, internal temperatures inside armored hulls could exceed 140 degrees Fahrenheit or 60 degrees Celsius, accelerating lubricant breakdown. Dust and sand, fine abrasive particles penetrated seals and housings, contaminating oils and greases. Constant vibration, tracks, uneven terrain, and weapons fire subjected mechanical assemblies to continuous shock loads. Limited maintenance access. Many components were buried deep within the suspension, drivetrain, or turret, making frequent servicing difficult in field conditions. Conventional lubrication systems struggled under these conditions. Grease-packed components tended to trap dust, forming abrasive compounds that accelerated wear. Oil-lubricated parts required regular inspection and replenishment, often impractical during extended operations or training exercises. British forces operating in North Africa from 1940 onward encountered similar challenges. Their tanks, such as the Matilda II, Crusader, and Valentine, required intensive maintenance schedules to remain operational in desert environments. Dust ingress and heat increased wear rates across many mechanical systems, placing heavy demands on crews and repair units. American armored units conducting training in arid regions, including facilities such as Yuma Proving Ground, Arizona, observed comparable patterns. Early U.S. tanks demonstrated that sustained operation in desert conditions significantly increased mechanical wear and maintenance requirements. The Army Ordnance Department explored multiple avenues to improve reliability, improved sealing methods, revised lubrication practices, and material upgrades. No single solution eliminated all problems, but the experience underscored the value of components that could operate reliably with minimal external lubrication and reduced maintenance dependency. At the same time, self-lubricating sintered metal bearings, such as Chrysler's Oilite bushings, already in civilian and industrial use since the early 1930s, were increasingly recognized across industry and military manufacturing as one effective approach for applications where regular servicing was difficult or impractical. The Army Ordnance Department contacted Amplex in 1940, requesting samples of Oilite bearings for military testing. Could they withstand tank operating conditions? The answer was yes, spectacularly so. Oilite bearings solved every desert problem: self-contained lubrication, oil trapped in pores couldn't leak out, couldn't be contaminated by external dust, heat resistance, bronze-tin alloy remained stable at temperatures that degraded greases, dust immunity. The bearing surface remained clean, no grease to attract and hold abrasive particles, long service life. Bearings operated thousands of hours without maintenance or replacement. Accessibility irrelevant. Since bearings didn't require servicing, inaccessible locations were no longer problematic. Testing at Aberdeen Proving Ground confirmed the advantages. Tanks equipped with oil-light bearings in suspension, transmission, and turret mechanisms operated in simulated desert conditions for thousands of hours without bearing failures. Production orders followed immediately. Amplex expanded manufacturing capacity dramatically to meet military demands. By 1942, the Oil-Light division was producing bearings not just for tanks, but for aircraft used in the Supermarine Spitfire, British, P-47 Thunderbolt, B-17 Flying Fortress. Naval vessels, propeller shaft bearings, steering mechanisms, gun turrets, military vehicles, trucks, jeeps, half-tracks, any vehicle operating in harsh conditions. Industrial equipment, factory machinery supporting war production. Amplex's war production statistics were staggering. The company saved hundreds of thousands of hours of machinist time during the war, producing high-precision, quality-centered products without waste, according to company records. The M4 Sherman tank, America's primary medium tank of World War II, used oil-light bearings extensively in its vertical volute spring suspension, VVSS. Each Sherman had 6 bogie units per side, 12 total, each containing multiple bearings. Bogie arm pivot bearings, where suspension arms attached to hull, road wheel bearings supporting the twin road wheels on each bogie, track roller bearings supporting return rollers for the track. Conventional bearings in these locations required frequent lubrication, grease fittings exposed to mud, dust, and water. In desert or muddy conditions, contamination destroyed bearings within days. Oil-light bearings eliminated this maintenance burden. The Sherman suspension could operate for weeks without servicing. When British forces received American-built Shermans for the North African campaign in 1942, maintenance crews were astounded by the reduced bearing maintenance compared to British-built tanks. General George S. Patton's Third Army, racing across France in summer 1944, pushed Shermans to their mechanical limits. Tanks operating 24 hours daily for weeks still had functioning suspension bearings thanks to Oil-Light's self-lubrication capability. The engineering behind Oil-Light was elegantly simple but required precise manufacturing. Material composition: 90% copper, 10% tin, less than 1% iron, trace amounts, sometimes graphite for additional lubrication properties. Manufacturing process: 1. Powder preparation. Metal powders ground to precise particle size, typically 150 to 200 mesh. 2. Blending. Copper, tin, and any additives thoroughly mixed for uniform composition. 3. Pressing. Powder pressed in steel dies under 20 to 50 tons per square inch, forming green compacts. 4. Sintering. Heated in controlled atmosphere furnaces, oxygen-free to prevent oxidation, to 780 to 850 degrees Celsius, 1436 to 1592 degrees Fahrenheit, below copper's melting point, 1085 degrees Celsius, but hot enough for atomic diffusion to bond particles. 5. Cooling. Slow cooling to avoid cracking. 6. Sizing. Sometimes repressed for dimensional accuracy. 7. Oil impregnation. Placed in a vacuum chamber, air evacuated, chamber flooded with SAE-30 oil, atmospheric pressure restored to force oil into pores. The result: bearings with approximately 25 to 30% porosity by volume, filled completely with oil. The pores, microscopic interconnected channels, held oil through capillary action, but released it when heat and friction reduced oil viscosity and expanded the metal slightly. Operating principle: when a shaft rotates in an oil-light bearing, friction generates heat. The heat causes oil viscosity to decrease, becomes more fluid, metal to expand microscopically, pushing oil towards surface, oil to migrate to bearing/shaft interface. When rotation stops and the bearing cools, capillary action pulls oil back into the pores. The bearing appears dry externally but remains fully oil-saturated internally. This cycle could repeat thousands of times over years of operation without the bearing running dry. When World War II ended, oil-light bearings transitioned smoothly from military to civilian applications because civilian applications had never stopped. By the 1950s, oil-light bearings were standard components in automobiles. Virtually every American car used them in multiple locations. Home appliances, washing machines, vacuum cleaners, fans, anywhere small motors needed bearings. Industrial equipment, factory machinery, pumps, conveyor systems, office equipment, typewriters, calculators, early computers, toys, electric trains, remote control cars, anywhere small bearings were needed. The Amplex Oil-Light division continued expanding. In 1961, a second plant opened in Trenton, Michigan. In 1965, sales hit record levels, 24% over 1964, and the division unveiled aluminum-based oil-light bearings for special applications. By 1996, the business had evolved through multiple owners. Sinter Metals Inc. purchased it, then was itself acquired by GKN plc in 1997. GKN became the world's largest powder metal component producer, with oil-light bearings remaining a flagship product. As of 2024, oil-light bearings are manufactured by Beamer Precision Inc. in Pennsylvania, which holds the registered trademark. The company continues producing bearings using processes fundamentally unchanged from William Sherwood's 1929 patents. In 2027, oil-light bearings will celebrate their 100th anniversary. From Carl Breer's 1927 inspiration to a product still manufactured and sold worldwide in 2027. The longevity is remarkable. Most 1920s technologies are obsolete, replaced by superior modern alternatives. But oil-light remains competitive because the fundamental physics haven't changed. Porous metal impregnated with oil is still one of the most effective self-lubricating bearing solutions. Modern applications include automotive, still used in specific locations where access is limited or maintenance undesirable, aerospace, Formula One cars, military aircraft, industrial robotics, actuators, joints requiring maintenance-free operation, medical devices, equipment requiring non-contaminating lubrication, consumer products, countless applications where reliability matters. Material variants have evolved beyond the original bronze. Super oil-light, an iron-based sintered bearing, harder and stronger than bronze, rated for higher loads but slower speeds. Oil-Light Plus, standard bronze impregnated with oil plus PTFE particles, reducing friction by approximately 17%. Aluminum Oil-Light, lightweight bearings for aerospace applications. But the original bronze-tin composition remains the most widely used, designated ASTM B438-95A Grade 1, Type 2, and SAE 841 in industry standards. In 1927, Carl Breer faced a simple problem, a clutch that slipped because oil contaminated an inaccessible bearing. His solution, a metal sponge soaked with oil, seemed absurd. General Motors had tried and failed. Conventional wisdom said it wouldn't work. But William Sherwood and Bill Calkins proved it could work. By 1930, they'd created bearings that held their own oil supply internally, releasing it only when friction heated during operation. By 1932, oil-light bearings were in production automobiles. By 1935, Amplex operated a massive factory producing millions annually. By 1940, when American tanks began overheating in desert training, oil-light was ready to solve a problem nobody had anticipated. The wartime contribution was enormous. Sherman tanks, P-47 fighters, Spitfires, naval vessels all used oil-light bearings in applications where conventional bearings failed. The technology kept armor mobile, aircraft flying, and ships operational in conditions that destroyed traditional lubrication systems. But the peacetime contribution was equally profound. Billions of oil-light bearings, manufactured over 9 decades, reduced maintenance costs, improved reliability, and enabled products that would have been impractical with conventional bearings requiring constant servicing. Today, nearly a century after Carl Breer wondered if metal could hold oil like a sponge, the answer remains yes. The oil-light bearing, porous bronze impregnated with lubricant through vacuum pressure, remains one of the most elegant engineering solutions ever developed. Simple in concept, metal with microscopic pores filled with oil. Sophisticated in execution, precise powder metallurgy, controlled sintering, vacuum impregnation. Effective in application, 97 years of continuous production, billions of bearings, applications from clutches to spacecraft. American tank bearings seized in 1940. Chrysler made sponge metal that oiled itself. And that self-lubricating bronze, invented to fix a slipping clutch, ended up helping win a world war and launching an industry that's still thriving today. That's the power of solving one problem well. The solution finds 1,000 applications you never imagined.